Okay, we're starting today with just a couple of problems related to recent homework. So we want to solve each of these equations. Now, this first equation two x minus 8, quantity 2x minus 8 times the quantity x plus 5 times the quantity 4x minus 7 equals 0. This breaks into three equations because the only way the product is going to be 0 is if one of these is 0. Okay, so if 2x minus 8 equals 0, then x is a solution. If x plus 5 equals 0, then that x would be a solution. If 4x minus 7 equals 0, then that x would be a solution. Taking the first equation, we add the equation 8 equals 8. And when we do, the negative 8 and the positive 8 are going to give us 0. And we're going to be left with just 2x over here. Now, I prefer to go ahead and write out the addition. Okay. We do the plus 8 added to the 2x minus 8 and the 0 plus 8. And then we simplify that and we get 2x equals 8. And then we divide both sides by 2. This 2, the 2 in the denominator divides the factor of 2 in the numerator. We have x then equal 4. So x equals 4 is a solution. Now, at least one person found that just by looking at this and said, well, okay, x equals 4, that's going to be 0. That's good, okay? But you might even be able to do that with this equation, but the equations can get more complicated. So you always want to write out the equations. And then really, even if you can do it by inspection, do the steps of solving the equation to reinforce them. So with x plus 5 equals 0, we're going to add negative 5 to both sides, which means we add the equation negative 5 equals negative 5, giving us x plus 5 minus 5 equals 0 minus 5. Well, 5 minus 5 is 0, so we just have x on the left-hand side, and 0 minus 5 is negative 5, and right there's another solution. Now that one, we would pretty much immediately solve by inspection. If it's just x plus something or x minus something, it's going to be pretty obvious to almost everybody what that number is going to be. And this one is fairly obvious. It's possible to figure it out. On this one, it's also possible, if you understand fractions well enough, to figure out what that ought to be. But most people are probably going to want to add 7 to both sides. And then you get 4x minus 7 plus 7 equals 0 plus 7. I recommend that you don't skip this step because I've seen people making terrible mistakes here, like adding the 7 to the 4. Okay? You won't do that if you write it out the way it is. Okay? So we have 4x equals 7, and now we simply divide both sides by 4. And we get perfectly good solution, x equals 7/4. The solution set then would be negative 5, 7/4, 4. So it's pretty simple to solve an equation where you have a bunch of things multiplied together equal to 0. If all those things are simply linear expressions with just x's and numbers, then it's really easy to solve, okay? Now, these expressions, some of them could be quadratic. They could be like this. If I threw this into this product, I would have to solve this equation. Now, this isn't part of this problem, but you understand that one of these, if I replaced 4x minus 7 by x squared minus x minus 6, then I'd have to solve this equation, wouldn't I? Okay, so sometimes you got to do a little more work to solve the equations than you do with linear equations. The linear equations are really pretty simple. They're easy to solve. If you're a little rusty, well, I'm sure it's come back to you, okay? Now, I'll just move the board over a little so I don't block it. X squared minus x minus 6 equals 0. That's of the form, well, here's our logic. We factored this into the form x plus a times x plus b. Now, if we do that, and if you remember the distributive law, we're going to multiply x by x plus b, and then we're going to multiply a by x plus b. And that's going to give us, well, I'll do it. The distributive law tells us that this multiplies everything here, and that this multiplies this factor, okay? That the x multiplies the x plus b, the a multiplies the x plus b, and that's exactly what I've written. And then the distributive law again, x multiplied by the quantity x plus b gives us x squared plus bx, and a times the quantity x plus b gives us ax plus ab. And of course, bx plus ax is just a plus b times x. Now you want to understand this so you understand why you do what you do. And what you have to do is you have to identify the numbers that have x's on them and numbers that don't. Well, this has an x squared, that's an x term, and then this has an x, but this doesn't. In this form here, the only thing that doesn't have an x is a times b. So that a times b has to equal -6. So a times b must equal -6. So the first thing we do when we try to factor we factor as x plus a times x plus b, where a times b is -6. What are numbers that multiply out to -6? Well, you can easily list all possible numbers that multiply out to -6. Okay, a could be 1, b could be -6. A could be 2, in which case B would be negative 3. Or A could be 3, in which case B would be negative 2. Or A could be 6, in which case B would be negative 1. Also, A could be negative 1 and B could be 6. A could be negative 2 and B could be 3. A could be negative 3 and B could be 2. However, negative 2 and 3 already exist here. It doesn't matter which one is negative 2, which one is negative 2, which one is 3. Since we have B equal negative 2 here, A equals 3 here, we don't really need to worry about this. And we have a 3 and a negative 2 here. It's the same as having a negative 3 and a 2, so we don't worry about that. We also have a 6 and a negative 1, so we don't need this. So now let's try it. Let's try letting A equal 1 and B equal negative 3. We get x plus 1 times x minus 6. So that's the same as x times x minus 6 plus 1 times x minus 6, which is the same as x squared minus 6x plus x minus 6, which is x squared minus 5x minus 6. Okay, well, this doesn't match. Put a little exclamation to that. It was a nice try, but it didn't give us a negative x up here, it gave us a negative 5x. Okay, well, let's try 2 and negative 3. This gives us x times the quantity x minus 3 plus 2 times the quantity x minus 3, which is then x squared minus 3x plus 2x minus 6. Minus 3x and 2x is just plain old minus x. So we have x squared minus x minus 6. Look at that, that matches. Okay, so we can say that x plus 2 times x minus 3 equals 0. And just as in the case over here, this splits into the equation x plus 2 equals 0 and the equation x minus 3 equals 0. And we don't need to do a lot of steps to figure out that if x plus 2 is 0, x has to be minus 2. And the solution to this equation is obviously x equals 3. Though I still recommend that you write out the steps. Now, another thing that I'd like to see people do is write the word or. Okay. This is satisfied if 2x minus 8 equals 0, or if x plus 5 equals 0, or if 4x minus 7 equals 0. So their solution is And I recommend that you write that word out whether you understand why or not. Because later on, the logic that's involved in solutions is going to involve a lot of ands and ors that you don't want to confuse. And I think, again, the habit of acknowledging the fact that it could be this, or it could be this, or it could be this. You wouldn't say and, because x equals -5, then it doesn't equal 7/4. It can't equal -5 and equal 7/4. Okay, it's an or. And you want to understand that about ands and ors. Okay, so that's pretty much where we're at. So if you're a little behind, get caught up. This isn't terribly difficult. But then, of course, if you're behind, it makes it a little harder to catch up. Now I want to move to something a little bit different. So I'm going to ask you just to add a couple of fractions. What's 5/8 plus 2/3? So what's the sum of these fractions? Well, I'm going to write this out in specific steps. Everybody got the right solution. Everybody saw that you're going to use a common denominator of 24 and correctly expressed both fractions as with denominator 24. And I think you got 31/24. Okay, everybody got that. Somebody's just writing the last little bit. They've written everything except the 24 in the denominator of the sum, and their hand was in motion. So I expected that worked out. So I think I'm pretty confident that everybody got it. Well, it equals this. Now, I don't know if you wrote down that step. I didn't look. I just saw, okay, you got the right denominator. You know how to add fractions, but you want to write out this step. And then that gives you 15/24 plus 16/24. Which gives you 31/24. Make sense? Okay. I'm gonna change that. I want to make this a little simple. It's going to make it A/B plus D/C. Now, what I just wrote down, we'll do next, but let's see if you can add this using the same ideas. You have symbols, you don't know what the symbols mean. It could be any number. But can you add these two symbolic fractions? Well, everybody did real well with that. It's great to see. Okay, we got A/B. And we're going to have to multiply that by something. Then we've got D/C, which will multiply by something. It's going to be a fraction, just by imitation with what we have here. Now, why did this work up here? It's because 3/3 is just 1. So really, when we multiply 5/8 by 3/3, we're just multiplying 5/8 by 1. just to make it look a little different, but this fraction has exactly the same value that this one does, okay? And because we multiplied this one by 8/8, we just multiplied it by 1. So the fraction that resulted was identical in value to the fraction that we started with. Okay, well, we want to get a common denominator. We want to get the same denominator. And everybody saw that we get this by multiplying this one by c over c, because the denominator has to have a c in it. So there we have it. And denominator also has to have a b in it. So we'd better multiply this one by b over b. Okay? So we multiply a over b times c over c, which will give us a times c over bc, plus then d over c gets multiplied by b over b, giving us db over cb. CB is the same thing as BC. So we'll write again AC over BC plus DB over BC, which is the same as what we had before. DB over CB is the same as DB over BC, because CB is the same as BC. So now we can add the numerators. And the reason we can add the numerators is simply because AC plus DB in the numerator is divided by BC. By the distributive law, then, AC is divided by BC and DB is divided by BC, which is exactly what the previous step tells us. So this is just a distributive law application. But there it is, and everybody's good with that. Okay, so I'm going to have a little more fun. Okay, we're going to do A over BE plus C over DE. Let's see what we can do with that. Getting a little more complicated. If you imitate what we did here, you could just multiply A over BE by DE over DE. And then multiply C over DE by BE over BE. In other words, I use the denominator here to make this denominator, and I use this denominator on the second term to make this denominator. You can see if that's going to work, right? That's going to give you ADE plus CBE, all divided by BDE squared. Now it's just a little bit of a step. My denominator here is BEDE. Well, BE times DE, we can put it in alphabetical order, B first, D second, and then two E's, E times E, that gives us E squared. Okay. And here, same thing, we're going to get CBE, and we're going to get a B, a D, and an E squared. Okay. Now, you could have done that easier. Here we got A over BE plus C over DE. We're going to multiply each of them by some fraction to give them the same denominator. This one already has a B and an E in it. The only thing that the second denominator has that the first doesn't is a D. It's already got E. So we don't need to multiply by E. We just need to multiply by D over D. We get BED. Over here, we got DE in the denominator. The first denominator has a B that the second one doesn't. So we're going to have to multiply by B over B. And that gives us AD plus CB over BDE. Putting the letters alphabetically here just so we can be sure we know what we have. Okay, now this is equal to the original expression. And so is this. It must then be that this equals this. That the thing we got when we, well, that the most recent calculation here is equivalent to this. That's so because if we take this, we can simplify it. We have an E in common between the two terms in the numerator. We have ADE and CBE. So we can multiply, we can express the numerator as AD plus CB times E. We could express the denominator as BDE squared, but that could be written as BDE times E. And you see that we have an E in the denominator as a factor of the denominator, and E as a factor of the numerator. So they can divide each other, and we just end up with AD plus CB over BDE. And this agrees with this. In our first attempt to get the common denominator, we just multiplied the two denominators. So our common denominator is going to be BE times DE. That worked. It gave us something perfectly good, but to put it in simplified form, we had to do a little more work. Here, we just created a denominator that contained both of the original denominators. The original denominators are BE and DE, so that our common denominator could just be BDE. BE is right there in the denominator. We've got a B times an E. And DE is in the denominator, and that's all that's necessary. So this is a common denominator. BDE squared is a common denominator. BDE is also a common denominator. It's got less in it than this one does. So we call it the least common denominator. And you can take that back to what you know about fractions, because y'all were pretty good with the fractions, okay? Well, now let's do one that looks a little more intimidating, maybe. How about if we have x minus 3 over x plus 5 added to x plus 2 over x minus 4. If you just keep your wits about you and do something very similar to what you've been doing, I'm fairly optimistic that you're going to be able to get this, but it looks a little strange. And don't let that throw you. Okay, again, we have x minus 3 over x plus 5 added to x plus 2 over x minus 4. We want a common denominator. Well, if we do this, write out x minus 3 over x plus 5 and multiply it by the denominator of the second fraction, x minus 4 over x minus 4, then our denominator will be x plus 5 times x minus 4. And if we do the same thing over here, multiplying x plus 2 over x minus 4 by the first denominator over itself. In other words, first denominator is x plus 5. We're going to multiply the x plus 2 over x minus 4 by x plus 5 over x plus 5. Then our fraction is going to be x minus 3 times x minus 4 over x plus 5 times x minus 4 added to x plus 2 times x plus 5 over x plus 5 times x minus 4. Now, when I did it originally, the denominator would be x minus 4 times x plus 5 if I did it in order, but that's the same as x plus 5 times x minus 4. So I've just reversed the order of the x minus 4 and the x plus 5, so it'll match the order of the denominator in the first equation, so we can see as clearly as possible that the denominators are identical. Having done that, we can write a fraction with the numerator equal to the sum of the numerators of the two fractions. All that over the same denominator, x plus 5 times x minus 4. Okay. And that's really no different than what we did on the very first problem. We just took the denominator of the second fraction and multiplied it by the denominator of the first fraction and the numerator of the first fraction. We had to multiply it by the denominator and the numerator, so we'd be multiplying by 1. There's more to do. We multiplied these out using the distributive law. Now I'm going to shortcut it. I don't have room to write out the entire distributive law. So I'm just going to write out what we get. Multiply x minus 3 times x minus 4. We get x squared minus 7x plus 12. If we multiply x plus 2 by x plus 5, we get x squared plus 2x plus 10. That's all over x plus 5 times x minus 4. And then we have an x squared in the numerator from the first product and an x squared from the second product. In other words, we have 2x squareds in the numerator, so we write 2x squared. We have a 7x and we have a negative 7x from our first product and a plus 7x from the second product. So we have no x's, negative 7x and 7x adds to 0. And 12 and 10 gives us 22. Now I've got 2x squared plus 22 is the numerator, x plus 5 times x minus 4 as the denominator. We generally want to factor the numerator if possible. And we can do a little bit of factoring in the numerator. We got 2x squared plus 22. We could factor 2 out of that. Say that's 2 times x squared plus 11. And the reason we factor the numerator as much as possible is it's entirely possible, it often happens, sometimes happens, that you get a factor of the numerator that matches a factor of the denominator and can be divided out or canceled. That didn't happen here, but you're going to see it in some examples. Pattern is what we've been doing. That's actually x plus 3 times x plus 5. But if you want to do x plus 5 squared, that's okay. I didn't write that 3 as clearly as I might have. So you can change it or you keep it as a five. Up to you. It's good one way as the other. Fractional Kansas. Keep the next step. Very good. So you can do the next step. Now we put it all as one fraction. Be back and get to that. Yeah. Then you multiply that out, put it all together, multiply that out, just have fun. We're not going to do that. But that can be done. All you need is a smooth. Okay. Okay, so again, we have x plus 2 over the quantity x plus 3 times the quantity x plus 5. numerator is x plus 2, denominator is x plus 3 times x plus 5. And the second one, numerator is 4x minus 7, denominator is x minus 3. We can do as we've done before. We can write down the first fraction and multiply it by x minus 3 over x minus 3, x minus 3 being the denominator of the second fractional expression or rational expression. I'm going to start calling these rational expressions. They don't, it's just fractions with symbols. Okay. And then we take second fraction and multiply by the fraction or rational expression where we have the first denominator over the first denominator. We got 4x minus 7 over x minus 3 multiplied by the denominator of the first fraction, which was x plus 3 times x plus 5 over the same thing, x plus 3 times x plus 5. And now we have, multiplying the numerators, we have x plus 2 times x minus 3, the numerators of the first fraction and the expression we just multiplied by, over x plus 3 times x plus 5 times x minus 3. Then plus 4x minus 7 times x plus 3 times x plus 5 over quantity x minus 3 is quantity x plus 3 times the quantity x plus 5. And it gets kind of long, but it's easy enough to write it out. Get a writer's cramp after a while. But again, we have x plus 2 times x minus 3 plus 4x minus 7 multiplied by x plus 3 multiplied by x plus 5 over the common denominator, which I'll write as x plus 3 times x plus 5 times x minus 3. Now there's still work to be done. We want to leave the denominator factor. We don't want to multiply these out at this point because we do want to multiply everything in the numerator out and then see if we could factor that expression and if maybe there's at least one factor in that expression that matches a factor in the denominator. It's unlikely on this problem because I didn't set it up so that it would be so, but it could happen. Okay, well, that's about it. There's more that I could say, and we've got a couple of minutes. But it would be, well, I'll just work the example. Okay, here we go. X plus 2 over x minus 4 times x plus 7 plus 4x minus 7 over x minus 4 times x plus 7 squared. Oh, what do you want to do? We'll make it x plus 4. Okay. Now, what does the second denominator, x plus 4 times the quantity x plus 7 squared, and the first denominator, which is x minus 4 times x plus 7, what does the second denominator have that the first doesn't? Well, it's got a square on that x plus 7, whereas the first one doesn't. Now that means it has an x plus 7 and times x plus 7, because that's what x plus 7 squared is. We need an extra x plus 7 in order to make the first denominator begin to match the second. So we've got x plus 2. And you know what I'm going to do? I'm going to keep this. Okay, I've just changed the second denominator to just be x minus 4 times x plus 7 quantity squared. But again, we need another x plus 7 in the denominator of the first equation, and we get it if we multiply the first rational expression. Okay, again, we need another x plus 7 in the first denominator. So we multiply the first expression by x plus 7 over x plus 7. And the second expression, well, it's already got x plus 7, so we don't need any more x plus 7s. It's already got an x minus 4, so we don't need anything. All we need to do is keep the second rational expression the way it is, because everything in the first fractional expression is already there in the second expression. We don't need anything more. So when we multiply this out, we get first fraction multiplied by the x plus 7 over x plus 7 gives us x plus 2 times x plus 7. And then that's divided by x minus 4 times x plus 7 times x plus 7, but that's just x plus 7 squared. And our second fraction is 4x minus 7 over x minus 4 times x plus 7 squared. Now the denominators match. And we can write out the numerator of the first fraction, which is x plus 2 times x plus 7, added to the numerator of the second fraction, which is 4x minus 7. And then that's divided by x minus 4, x plus 7 squared. And that's our denominator, x minus 4 times x plus 7 quantity squared. Again, we'd have to multiply out the x plus 2 times x plus 7 in the numerator and simplify that down to simple, to single polynomial. And then try to factor it and see if any factors match factors of the denominator. Okay? But there's the process for adding any two expressions. You'll see more examples, and of course the homework. We'll give you just a little more information, and then we'll see how we're doing next time.